So hello, everyone. Thanks for the introduction. Today, I'm going to talk about a new primitive we propose in this work, referred to as oblivious issuance of proofs. I will start by explaining what it is and why it is used for. So let's first recall the concept of non-interactive proofs. So given a relation R and its corresponding language L, assuming that Alice holds the witness for a statement X in the language, and Bob wants to know whether the X is indeed in the language. And then Alice can try to convince Bob by sending a single message, and Bob decides whether to accept or reject. So we say pi is a non-interactive proof if the Bob will always accept if the Alice holds the correct witness, and Bob will always reject if X is not in the language. For example, the proof can be just a witness. So to make the problem non-trivial, we really consider additional properties such as zero knowledge. And in this work, we consider an orthogonal problem. That is whether we can issue this proof obliviously. So more precisely, we want to construct an interactive protocol that allows Bob to obtain a non-interactive proof, which can be verified by anyone, and while keeping this proof hidden from Alice. And moreover, a part of X remains hidden from Alice too. We refer this property as obliviousness. So which means that the proof and the hidden part of X cannot be linked to the interaction. And proof here retains the same property as before. And moreover, we require the protocol to be one more forgeable, which means that Bob cannot forge more proofs than the numbers of issuing interactions. So why do we want to obliviously issue proofs? The motivation is that it can be used to construct blind signatures and anonymous credentials. I will explain them one by one. So a blind signatures protocol allows Bob to obtain a signature from Alice with a secret key, while keeping both message and signature hidden from Alice. The property is known as blindness, which means the message and signature cannot be linked to the interaction. And we also want one more forgeability, means the Bob cannot forge more signature than the numbers of issuer interactions. Blind signature is very useful. It was originally proposed to construct anonymous ECAS system, and they're now widely used in network services to achieve anonymity and also protect user privacy. So you can see here that the syntax of blind signature is closely related with that of the anonymous oblivious of proofs. So in fact, if the signature can be viewed as a proof, and blind signature scheme can be viewed as an oblivious issuance protocol for certain proofs. In fact, the variety of blind signature schemes and their extensions have this property. For example, the blind Schnorr signature can be viewed as an oblivious issuance for proof of knowledge of discrete logarithm. And in turn, we can construct oblivious issuance protocol for general proofs, and it will open doors to new construction of blind signature. So another use case is in anonymous credentials. So in this scenario, the user wants to obtain a credential from an authority for a set of attributes. And later, the user can present the credential and a set of attributes to a verifier in an anonymous way, which means that the showing cannot be linked to the issuance. And also, the user can present its credential multiple times where each showing is unlinkable. And in addition, the user can only review a partial information about M while keep the rest hidden. So this primitive is referred to as a multi-show anonymous credential. And however, one limitation of the current construction is that all existing scheme relies on pairing friendly curves, practical scheme, and which make them undesirable for many applications due to the lack of good library support. So a simpler scenario arises when the user only needs to present the credential to the issuer, which means the issuer also plays the role of verifier. So one note that In this case, the issuer needs to additionally send a proof that the credential is computed correctly. So this primitive is referred to as a key verification anonymous credential, which was first proposed by Chase in 2014. It also gives construction based on parent-free groups that offer better efficiency and are now used in signal encrypted messaging. And however, the drawback here is that they do not offer unlinkable public verification. So one question is whether we can add this feature to this system. And we show that with oblivious issuance of proofs, we can do a single unlinkable public show. So the idea is to replace the original issuance protocol with an oblivious issuance protocol, such that the user can obtain a credential and a proof that is unlinkable to the issuance. And to do the unlinkable public show, the user simply send a credential and proof together with proof of knowledge of the hidden attributes to the verifier. And however, the user cannot do this showing unlinkable twice because the two different showing can be linked. So this primitive is also known as single show anonymous credential. And the nice thing about constructing here is that we do not disturb the original key verification functionality, which means that the presentation of the credential to the issuer remains the same as before. And there are only minor changes to the original protocol, and it's only in the issuance part. So I'll now review the related works. So we can construct this oblivious issuance of proofs using the idea of meta proofs, where the user can create a zero knowledge proof of the statement that there exists a proof that makes verification algorithm accept. So then the zero knowledge property guarantees a new proof is unlinkable with the original one. However, this is not efficient due to either the high computational cost or the large signature size. Another way is to use a randomizable proof, where the user can randomize the proof to an unlinkable version. However, here, the construction is based on the gross high proofs, which relies on pair. And also, as mentioned earlier, the blind Schnorr signatures can be viewed as an oblivious issuance of certain proof. And the construction is efficient and based on pairing-free group. However, a recent text showed they are not one-more forgeable in the concurrent setting. And there is an ongoing efforts to avoid the attack. And nonetheless, they all consider proofs for certain relations. So the main question we address in this paper is whether we can issue proofs obliviously for more general relations based on pairing-free groups. And our contribution can be summarized as follows. We first give formal syntax and security notions for this primitive. And then we give parent-free constructions for a linear class of linear relation, which referred to as an algebraic relations. A note here is that a security proof relies on both a algebraic group model and the random oracle model. And the application of our construction are twofold. The first is we give new construction of blind signatures and anonymous credentials. Another is that they can use to add unlinkable public verification to several existing systems. So for the rest of talk, our first goes through the syntax and security, and then introduce the algebraic relation, and finally give an overview of our constructions. So first of all, we consider the relation of the following form, where a statement can be divided into three components, where the X is the public part, while the Y and Z part are hidden from issuer. And the user can choose the Y part freely, while the final Z part is depending on both the witness and the Y part. So I hope this will become clear after I go through the syntax of the issuance. So we consider two modes of assurance. The first one is called free mode, where the user can choose this Y part freely, independent of the witness. So, and after an interaction, the user could obtain the corresponding Z part and a proof that shows that X1Z is in the language. Another mode is called restricted mode, where the user cannot choose the Y freely, but instead it can choose some public information that determines the distribution of the final Y. And in terms of security, for both mode, requires soundness, which guarantees that cannot forge a valid proof if the statement is not in the language. And also obliviousness, which guarantees that YZ and the proof cannot be linked to the interaction that issues them, even if the issuer is malicious. And for one more forgeability, it is defined using the following game. So where the initially a pair of W and X is sampled, and the adversary is acting as a malicious user with input X and can engage in L concurrent sessions, where the concurrent means that the interaction between different sessions can be arbitrarily interlinked. And the goal of the adversary is to output L+1 distinct tuples satisfy that for each proof pi I is valid for the statement that the X and Y and Z are in the language. And one remarks here that this one more forgeability is different from the soundness. I've now introduced the algebraic relations. So given prime order cyclic group G and the matrix, and by M matrix in the G, we can define an algebraic relation parameterized by the G and the matrix in this way. So here I use additive notation for group operations. So here the witness is a vector in ZP and the X is a vector in G. And they satisfy these following linear relations, which can be represented compactly using a matrix equation. And we see that these capture many common linear relations and can be proved by the sigma protocol. For example, a typical example is this DL-EQ relation, which consists of a scalar. So the witness is a single scalar, and the statement is 3 scoop elements. This can be seen as a special case of the algebraic relation, where the M is a 1-by-1 matrix. So I'm now given an overview of our constructions. So let's start with the scenario where we do not require obliviousness. So for simplicity, let's consider the example for the DL-EQ relation, and we focus on this free mode. So without the obliviousness, the user can simply send the Y to the issuer, and the issuer sends the correct Z back, and then they engage in the sigma protocol as shows that for the DL-EQ relation. And the soundness of the proof is due to the soundness of sigma protocol plus the Shamir transform. And then we want to how to achieve obliviousness. So first of all, to hide Y, the idea is that we can generate, we can multiply the Y by a random mask and result in Y prime. And then we send this Y prime to the issuer, and then the user can recover the correct Z by from Z prime by dividing out the V prime. So here the red denotes the random mask, and the blue denotes the parts of elements that is hidden from the issuer. And then to make the sigma protocol oblivious, we use an approach similar to the blind schnorr. So I will now delve into details here, but we can show is that it satisfies perfectly obliviousness if the Z prime is computed correctly. And due to the soundness of pi, the guaranteed Z prime is computed correctly, we can show is oblivious and in the random order. But it does scheme one more forgeable. Unfortunately, the same RS attack applies here, which means we can construct an adversary that can forge 1 plus log P forgeries by starting only log P issuance sessions. So at a high level, it is mainly due to the linearity of the protocol, which allows the adversary to easily combine components from different sessions. To avoid the RS attack, we utilize the idea from the prior work. So here, for simplicity, only consider do not consider obliviousness. So the core idea is that the issuer will sample a commitment of a random value E, and then the issuer compute the response the same as before, except the seed is now times by the E, and the issuer send the opening of the commitment back, and then it will also add to the proof. So now delving to the details of proof, but the core idea is that this multiplication of E breaks the linearity, which is crucial for the ROS attack. And we can show that the soundness now relies on the binding property of the commitment, which relies on the discrete log assumption. And following the similar diagram as shown in previous slides, we can also achieve obliviousness and prove it on the discrete log assumption. And for one more forgeability, I show the following. We show the following theorems. So in the free mode, we show this the scheme is one more forgeable for the DLEQ relations, and security is reduced to the strong DV-Hellman assumption. So here the QI represent the numbers of signings, and QH represent the numbers of issuing queries, the random queries. I will not go into much details here. And then for the restricted mode, I can show one more forgeability for any arbitrary algebraic relations. And to conclude, so we propose this oblivious issuance of proof in this paper, which can be viewed as a generalization to the blind signatures. And we give paradigm-free construction for algebraic relations, and which implies several applications. So in terms of future works, it would be valuable to explore whether we can extend our construction to more relations, and also whether we can construct oblivious issuance protocols for more kinds of proof like snarks. And also it would be interesting to see whether there are other applications. So that's all for the talk. Thank you for listening.
Okay, are there any questions? Yeah. Is there a microphone? I don't know. Is there a microphone?
Thanks. Is that working? Yes. Thank you for the nice talk. At the risk of this being a stupid question, how is the witness hidden from the user in your protocol? I guess does the witness need to be kind of if the user now learns the witness, they can probably forge, right?
Yeah, right.
So I was wondering, like in your protocol, why can't the user just multiply by the inverse of y to get the witness?
So first of all, I don't think the construction will leak the witness. And it is true that the one more forgeability, so we need to get, so it only holds if the adversary do not know the witness.
Okay, so let's thank the speaker again.
Is it on? Okay.
Okay, so for the next talk, we have amplification of non-interactive zero knowledge revisited, and the speaker is going to be Nathan Geyer.
Okay, so let me how do I switch? Okay, thank you. Okay, hi everyone. Thank you for the introduction. My name is Nathan, and I'm here to present a joint work with Nir Bitansky on amplification of non-interactive zero knowledge, or in short, NIZK. So security amplification is a foundational problem in cryptography. The goal is given a cryptographic primitive that is in some sense weakly secure to make it strongly secure. One central motivation to think about it is that weak primitives are often just simpler to construct. And I think two of the most famous examples in the context of hardness amplification are perhaps Yao's amplification of weak one-way functions and Yao's Sol lemma. And now today we are going to focus on the primitive NIZK. So what is NIZK? Just a reminder, the goal here is for the prover to convince the verifier in the validity of some NP statement without revealing anything about the witness. In addition to that, we don't want to have any interaction from the verifier, so we will be thinking on the CRS model, where initially there is some setup phase where a trusted third party generates a public common reference string, gives it to both parties. Then the prover sends one message to the verifier, which either accepts or rejects. Now we want an NIZK to have three basic properties. The first one is completeness. If the honest prover holds a true statement with an accepting witness, then the verifier should accept. The next one is soundness. For every malicious prover, we want that the probability for the prover to cheat, that is, to generate a false statement with an accepting proof, should be negligible. Now here there are actually several different variations to soundness. For example, you can think about a soundness against any prover, including an efficient one, and then you have statistical soundness or proofs. And you can also choose to restrict your attentions only to soundness against efficient provers. Then you have computational soundness or arguments. In addition to that, in this talk, we will only be focusing on adaptive soundness, which means that the cheating prover may choose the statement after seeing the CRS. Now, the last property is zero knowledge. We want there to exist an efficient simulator such that the real view of the verifier is computationally indistinguishable from the simulated view generated by the simulator, giving only the statement without ever seeing the witness. Now, when we refer in this talk to weak NIZK, we mean weak soundness and weak zero knowledge. So more specifically, when we refer to epsilon s, epsilon z, weak NIZK, what we mean is that the probability for the malicious prover to cheat is at most epsilon s, and the ability to distinguish between the real view and the simulated view is at most epsilon z. So you should think about both of them as some fractions between 0 and 1, for example, 1/3, 1/3. Now, I want you to notice that in some cases, for some parameters, weak NIZK is trivial. For example, a 1-0 weak NIZK with no soundness and perfect zero knowledge is trivial because the prover can just send nothing and the verifier always accepts. As a 0-1 weak NIZK with perfect soundness and no zero knowledge is also trivial because the prover can just send a witness in the clear. Now, this implies that every convex combination, right? Every P1-P weak NIZK is trivial because you can have in the CRS a p-biased bit indicating which of them to run. So therefore, we focus our attention only on the interesting case where the sum of errors is at most 1, is less than 1. Okay, otherwise, we don't really expect to be able to amplify because it would be the same as constructing NIZK from scratch. All right. And now, previously, Goyal, Jain, and Sahai studied this problem and suggested a way to amplify NIZK for any two constants with a sum smaller than 1. Their approach is based on the MPC in the head paradigm, and it requires sub-exponentially secure public encryption. But eventually, they have discovered a gap in their proof. Now, for our results, we show that you can amplify NIZK arguments for NP assuming only polynomially secure public encryption, and you can do that also for any constants with a sum smaller than 1. Now, in the setting of proofs, you don't need public encryption anymore. You can do that just assuming one-way functions. So we can amplify NISQ proofs assuming only one-way functions for the same range of parameters, for any two constants with a sum smaller than 1. And finally, public encryption is also not necessary when you are only trying to amplify zero knowledge in the case of arguments. So if you have NISQ arguments with negligible soundness error and you are just trying to amplify zero knowledge, then one-way functions are sufficient. Essentially, we only need public encryption in order to amplify computational soundness. So whenever you don't need to do that, one-way functions are sufficient. Our approach is based on the hidden bits paradigm. And in some sense, it is a reduction from zero knowledge amplification to the better understood problem of pseudo-randomness amplification. Now, I just want to mention that we are currently not aware of natural constructions of weak NISQ from weaker assumptions, except for just one example in a recent work where they construct weak non-interactive statistical zero knowledge from batch arguments. But still, I want to say that in some sense, weak NISQ always comes up naturally, for example, in the setting of combiners, because let's say, for example, that you give me 3 NISQ candidates, each of them based on a completely different assumption. And I want to combine them to one candidate such that even if one of the assumptions is false, it will still be secure. So one way I can do that is just pick one of them at random. Then I get a weak NISQ, which I can amplify. So an amplifier always gives you a combiner, which I think is natural to think about. And lastly, we just view NISQ amplification as a foundational hardness amplification problem. It is often not trivial how to amplify more advanced primitives. Okay, let's move on to the technical overview. So the general outline of what the proofs look like is this. First, we show a zero knowledge amplifier that exponentially reduces the zero knowledge error to epsilon z to the power of k, where k is some amplification parameter that we choose. But on the other hand, it increases the soundness error. As you can see, actually, the distance between 1 and the soundness error also reduces exponentially. So it gets closer and closer to 1. So it decreases the zero knowledge error, but increases the soundness error. Then we show the corresponding soundness amplifier, except that it's not exactly a soundness amplifier, it's a soundness star amplifier, which is a somewhat stronger notion that I will not elaborate on. Then we show how to combine the amplifiers. So because each of the amplifiers decreases one property, decreases one error, and increases the other, then we need to carefully combine them in order to reduce both of them. We want to reduce both of them to negligible. And finally, we observe that in the setting of proofs, you can get soundness star for free without any additional assumptions. And in the setting of arguments, you can always upgrade plain soundness to soundness star, assuming public encryption, which is the only place where we use public encryption. Okay. But for the rest of the talk, I'm only going to focus on the first part, on the zero knowledge amplifier. And you can even assume for simplicity for now that the soundness error is negligible and we are only trying to amplify soundness. So let's see what that looks like. So to this end, we are going to think of the primitive of a hidden bits generator. So essentially, this primitive is a PRG along with subset consistency proofs. That is, for every subset I that you choose of the output, once you draw a random seed, and then you reveal the output bits corresponding to subset I, along with the consistency proof, then all the other bits should remain pseudo-random. Okay, this is the primitive of an HBG. And the point is that it is sufficient for constructing NISQ. Okay, now I want to remind you that our goal is to amplify weak NISQ. That is, we want to construct NISQ from weak NISQ. So now we see that it's sufficient to construct an HBG from weak NISQ. Okay, this will be sufficient for us to construct an HBG from weak NISQ. Now, I first want you to notice that if we had strong NISQ, then you can easily construct an HBG from PRG plus strong NISQ, because you can simply use the strong NISQ to generate the subset consistency proof. And due to the zero knowledge property of the NISQ and the security of the PRG, you get that all the other bits are pseudo-random. However, we don't have a strong NISQ, we want to construct it. So the question is, what happens when you use a weak NIZC and how to fix that? So when you only use the weak NIZC to generate this subset consistency proof, you may leak some information about the seed. So you may leak some information about all the other bits. They may no longer look pseudo-random. And now we need to fix that. So I think maybe the most natural first attempt is to just take k independent copies and take the XOR. That is, draw k independent seeds, apply the PRG to each of them, and then take the XOR. Now, when you want to reveal the subset corresponding to the output bits corresponding to subset I, along with the consistency proof, what you can do is you can reveal subset I of every PRG, right, of every PRG application to every seed, along with the consistency proof for that seed. So this approach somewhat works in the sense that for some parameters, it does amplify zero knowledge, maybe not as fast as we hope, but it does amplify. But for some parameters, you don't get any amplification at all. For example, if the weak NIZC always if the weak NIZC always leaks the last bit of the PRG, then no matter how many times you take the XOR, it's not going to help you at all. You will still know the last bit of the outputs. So this approach is inherently limited to epsilon z, which is smaller than half, because if the weak NIZC proof only leaks one bit, the simulator can always guess it with probability half. So the instance where the weak NIZC always leaks the last bit of the PRG is a half ZK NIZC, and you don't get any amplification at all. Okay. Now, a similar problem comes up in the setting of weak PRG amplification, where Maurer and Tesaro show how to solve it using the concatenate and extract approach. So what they do is, instead of taking the XOR of the k copies, they concatenate them and then apply a strong extractor. So this way, you can amplify weak PRGs even when their distinguishability from one uniform is more than half. However, this approach does not immediately work for us because we also need to support the functionality of revealing a subset of the output without revealing anything about all the other bits. Now, here it is not clear. Let's say that I want to reveal to you subset I of the output of the extractor. It's not clear how to reveal only a subset of the PRGs that will let you learn exactly that and nothing more, right? For all you know, maybe only computing the first bit of the extractor already depends on all the output bits of the PRGs. Okay, so, but we can fix that. And to fix that, we do the following. So in this slide, I'm going to switch from a PRG to a PRF with an N output with PRF, but this is mostly done for the sake of notational ease. You can still use a PRG and divide its inputs into blocks. I just think that the PRF is more convenient to think about here. So we're going to have this table with k rows corresponding to k independent seeds and t columns corresponding to the number of hidden bits. You should think of t as just some polynomial, maybe n to the power of 7. Okay, so t is the number of hidden bits. And for every row, what we are going to do, we are going to apply the PRF with the corresponding seed on all natural numbers between 1 and t. So for every hidden bit, we are going to generate a pseudo-random block of size n. And we do this for every seed. Now, finally, the hidden bit string, in order to compute the hidden bit string, for every column corresponding to every hidden bit, we are going to concatenate all k blocks of size n of this column and use a strong extractor with 1 bit output. So from every column, we extract just 1 bit, and this is how we construct the hidden bit string. Okay, now, just for a sanity check, notice that if I reveal to you all the columns corresponding to subset I, then all the other columns due to the security of the PRF are pseudo-random, and then all the extractions are also pseudo-random. So the other bits are also pseudo-random. But of course, this is not enough for us because we also have the leakage from the weak NIZC proofs, right? In order to, what I need to do is not only reveal the columns corresponding to subset I also need to give you consistency proofs. So what I do is for every row corresponding to every seed, I give you a consistency proof that all the blocks I reveal to you in this row are consistent with respect to some seed. Okay, so I give you k consistency proofs. So this is the construction. And I'm not going to elaborate too much on the analysis. I'm just going to give you a quick informal overview. So what you can show is this. Every proof, I will say that the proof is good if it leaks only at most a constant number of bits, where this constant depends on epsilon z, but it's still some constant. Now, what you can show is that each proof is good, except for probability at most epsilon z. So the probability that no proof is good is at most epsilon z to the power of k, which is what we amplify to. Now, given that at least one proof is good, right? If even one row is good, then what I can say is that all blocks in this row, initially they had n bits of pseudo randomness. Then you take away at most a constant number of bits that you leak. So maybe they no longer look pseudo random, but they still have high pseudo average mean entropy. And then all the extractions work, because in every concatenation, there is at least one block from a good row. So this is just the idea that if even one proof is good in the sense that it doesn't leak too much, all the extractions work and you get the other bits are pseudo random. Okay, so finally, we have 3 open questions. The first open question is how to amplify when the gap of the sum from 1 is polynomially small, for example, half and half minus 1 over n. We only know how to do it for constants. The second open question is how to amplify zero knowledge when you only have non-adaptive soundness. Okay, notice that here, right, all the consistency proof referring to pseudo-random blocks that are chosen by the prover, right? The prover gets to pick all these blocks, and then it proves, and then it argues something about these blocks that it chose itself, which is why we need adaptive soundness. We currently don't know how to amplify zero knowledge without adaptive soundness. And finally, the last open question is how to amplify Nizek arguments without assuming public encryption, which is something that we only need to amplify computational soundness. We currently don't know how to amplify Nizek arguments without it. Okay, thank you very much.
Okay, any question? Yeah. Want to come here?
Yeah, thanks for the talk. I was just kind of interested in asking, these like weak non-reactive zero knowledge proofs, are they like easier to construct? Like, do you get them from like weaker assumptions, or like really what is the motivation of studying this amplification theorem in the first place? Because I think you mentioned that we only have constructions like statistical non-reactive zero knowledge.
Yes, so we currently don't know of specific constructions where it's easier to construct a weak Nizek from fully fledged Nizek. So this is an open question that you can think about. We currently are not aware of such constructions.
Okay, sure, thanks.
Okay, let's thank the speaker again. To the next speaker.
Remote control.
Green button. Okay. Okay. Okay, so for the next talk, we have a CDS composition of multi-round protocols, and the speaker is going to be Zehua Shang.
Thanks for the introduction. And hello, I'm Zehua Shang. And I'm honored to have the presentation of our paper CDS composition of multi-round protocols here. And this is joint work with Masayo Kiabe, Andrei Bogdanov, Miyako Okubo, Aaron Rosen, and Meditivity. So our starting point is Sigma protocols, where a prover convinces the verifier that he knows the witness that satisfies some relation R corresponds to some statement X by exchanging three messages, first message A and challenge E and response Z. And it has three basic properties, for example, completeness, two special soundness, and honest verified zero knowledge. Where the two special soundness means that there exists a structure that given any two accepting transcripts with the first the same first message and different challenges, we output witness W. And the Sigma protocols has also some generalizations to multi-round and case special sound public or interactive proofs. Next, let's take a look at this OR composition. So this kind of OR composition will work when we want to prove the relation that we know some witness, one witness out of two statements. And the general idea is that for the transcript that we had, we know the witness, we run the Sigma protocol honestly. And for the transcript, we don't need know the witness. We use a zero knowledge simulator to simulate a transcript with the randomly sampled challenges. And after computing the challenges for the real parts, we will complete for the remaining protocols. And it has some properties. For example, it has a linear proof size, and it preserves the same soundness and zero knowledge property as of the atomic statements. And also, if your statements for simulation is already known, then your simulation is fully pre-computable. Okay, so this kind of OR composition can be generalized to satisfy to more general access structure. For example, you want to prove that you know witnesses out of n statements that satisfies access structure that can be expressed as a monotone span program. And here you want to replace your addition with secret sharing schemes for those structure gamma star. And talk about the generalization of the Sigma protocols. So basically, we have two directions. The first direction is to generalize the special soundness from two special sound to k special sound. And another direction is that we will increase the number of rounds. So why we use such generalizations? A very important reason is that such generalized protocols may have better efficiency. For example, many snarks, which has a multi-round K1 to the K mu special soundness shape. And also there is a complex Sigma protocol presented by Atema et al. Which transforms the Sigma protocol into a multi-round K special sound version with logarithm communication complexity. And here comes the question that does our composition applies to those generalized 2 mu plus 1 round K special sound protocols? And it turns out that even you only want to generalize your protocols for only one direction, then for example, you have a 3 round K special sound protocols, or you have a 2 mu plus 1 round 2 special sound protocols, then even all proof will not work. So neither of the generalizations work below. So let's take a closer look at why this CDS composition fails. So here is an example of 3 special soundness protocols with a challenge space of 0, 1, and 2. And the cheating prover is able to ask up to 2 challenges. And it turns out that for our proof, the prover is able to adaptively answer the challenges by restricting each transcript challenges only a part of the challenge space. For example, when the verifier sends zeros, then the prover will answer with 0, 0, and sending 1 answer with 1, 0, and sending 2, 0, and 2. And it turns out that the extraction will fail because the extractor does not collect enough challenges. Okay, both will fail. And another example is for why this multi-round generalization will fail. So let's take a toy example of 5-round protocol for relation x1 and x1 prime. So in fact, it is a sequential composition of 2 sigma protocols, and you merge the third round and the next sigma protocol's first round. And for the extraction of the sigma protocols, you will extract a witness of W1 from the first 3 rounds. And also, you will extract W1 prime for the last 3 rounds. And here you will get a witness of W1 and W1 prime, which is exactly a witness for relation x1 and x1 prime. Okay, so for our proof for such composition, here, the extraction for the first 3 rounds is able to extract at least one of the witnesses of x1 or x2. And the same happens for the last 3 rounds. And what the extractor expects is that it wants to extract 2 witnesses on the same side. For example, here, the extractor will extract W1 and W1 prime. And this W1 and W1 prime is exactly the witness of this OR relation. But however, suppose that the prover has all witnesses, then the cheating prover is able to answer the challenges in the other side. And it turns out that the extraction will extract W1 and W2 prime, which is not a witness for our proof, and the extraction fails. So here comes our result. So in fact, we generalize the CDSL composition framework, and our framework for 2mu plus 1 round K1 to the K mu special sound public or interactive proofs, and which satisfies the access structure of monotone NC1 circuits. The observation is that this CDS fails because the prover is given too much freedom on choosing challenges. And our approach is to let the prover commit to the simulated challenges. Well, in fact, we use dual mode commitments. Such a commitment can be constructed in plain model from, for example, DDH assumptions. And for binding mode, it can have perfect binding properties. And in hiding mode, it is equivocable, and it has a mode indistinguishability. And what we need to prove that is that if the challenges are used for simulation, then the commitments for the challenges will work in the perfect binding mode. And also, we need to guarantee that all of the commitments are indistinguishable among our positions. So here is an example of 5-round outproof of our composition. So the basic idea is that we add a commitment for each transcript at the beginning. So for the transcripts that we don't have the witnesses, we let the commitment commits to the previously randomly sampled challenges. And for the part that the prover honestly runs the protocol, we let the prover commit to zeros. And after infection, the prover gets the challenges needed. It will equivocate the commitments for a new commitment information. And also, in additionally, we would attach a subproof in parallel to prove that at least one of those two commitments are in the binding mode. So such a subproof will get more complicated when we want to prove for a set structure beyond the simple R. For a simple R relation, we only need to prove that at least one of the commitments are in the binding mode. But for a general access structure gamma, what we want to prove is that our binding mode commitments are in some structure, which is gamma prime. So what is gamma prime, and what's the complexity of gamma prime? And we will call this gamma prime, which is the adversarial access structure. The name is because it represents for the simulated transcripts, which is opposed to where the prover has a witness. And on the negative side, we prove that if we're assuming that NP is not contained in Q-such poly, then for some access structure gamma in a monotone span program, the adversarial access structure will blow up in the circuit size. And on the positive side, we managed to prove that if the access structure gamma is computed by a read once formula, for example, monotone NC1 circuits, then our adversarial access structure gamma prime can be computed in polynomial time. And it turns out that this monotone NC1's complexity has already contained many useful access structures. For example, T-autofen threshold, or more generally thresholds of thresholds, or more generally some kinds of ranked choice voting. Okay, in the end, here is also a small issue where we want to use a secret sharing scheme applying to those status composition schemes. That is, the share size often exceeds the maximum length of the challenge space, since for Sigma protocols, the challenge space may be very small. And the traditional solution is that we use a parallel repetition, which extend the challenge space from C to the C to the T for T parallel repetitions. And this works for two special sound Sigma protocols very well, because no matter how many times you parallel repeat your two special sound protocols, it will preserve two special sound after your parallel repetition. However, the fact is that this case special soundness does not preserve in parallel repetition. And the result is, the fact is that after T parallel repetition, your special soundness will become K-1 to T plus 1 special soundness, which is exponential blow up. Okay, so we introduced a relaxation of such K-special soundness, which we call the statistical K-special soundness. And the observation is that the number of bad transcripts out of the all transcripts are negligible. So here the batch transcripts. So we mean that the transcripts that in some round there are some same challenges appears, or there are some additional rules that the challenges do not satisfy. Okay, so our definition is that there is a structure that's given accepting transcript, then it will fail to extract witnesses only for a negligible probability kappa. And this kappa depends on the choices of the challenges. Okay, and we may prove that the K1 to the K-mu spectral soundness after T parallel repetition is a statistical K1 to the K-mu spectral soundness. And it is remarkable that there is a very similar notion that is introduced in a paper that also accepted in this conference. Okay, so in the end, we come with a conclusion. So we introduce general CDS composition for multi-round public core interactive proofs. And our framework works in plane model. And we preserve the simulation computable properties. And we preserve the soundness and the number of rounds as of the atomic public core protocols. And our framework accepts structures belongs to a monotone C1. And also, in the end, we introduce statistical K1 to the K-mu spectral soundness definitions, which may be of independent interest. Okay, and that's all of my talk. And thanks for listening.
Any questions? Okay, I have a quick question.
Please.
Hey.
Oh, sorry.
So in the end, can you apply the Fiat-Shamir transformation to the final protocol that you obtain?
Can you say one more time?
I mean, because if I understood correctly, you need to relax the special soundness condition. So I'm asking whether then you can apply Fiat-Shamir to the multi-round protocol that you obtain at the end.
Well, okay, speak more slowly.
No.
Sorry.
So at the end, right, in the final protocol that you obtain after you compose the CDS protocols, right? You're gonna obtain a multi-round protocol, which, if I understood correctly, satisfies a weaker special soundness guarantee, right? The statistical.
No.
Or is it like sufficient to instantiate Fiat-Shamir? This is the question.
Yes, statistical special soundness is already implies knowledge soundness, but if your atomic protocols is perfect spectral sound, then after composition it is still a perfect spectral sound. If your atomic protocol is statistical spectral sound, then after composition it is still statistical spectral sound. So it preserves the same soundness.
Okay, thank you.
Okay,
Let's thank the speaker again. Okay, so for the last talk of this session, we have Black Box and Fast and Non-Malleable Zero Knowledge, and the speaker is Michele Ciampi.
Okay, thank you for the introduction. Yeah, this is a joint work with Vincenzo Botta, Ivan Visconti, Luisa Siniscalchi, and Emanuele Orsini. So before talking about non-malleable zero knowledge, let me recap a bit what is zero knowledge. So we learn that a protocol that is zero knowledge must enjoy like these two additional properties, which is completeness. So we have two parties, the prover and the verifier, and the prover runs with an additional input, which is the witness that it uses to convince the verifier about the validity of an NP statement X. Okay. So the other non-trivial property we want is that the property of soundness. So if the prover is corrupted, then there is no way that an efficient adversary should be able to convince the verifier about the validity of a statement X when X actually does not belong to the language. And zero knowledge means that whatever an adversarial verifier can learn by interacting with an honest prover that uses the witness to generate the transcript. Actually, the same can be learned by a process that we call a simulated process that doesn't use the witness at all, okay? So as long as these two outputs are indistinguishable, this means that your protocol is zero knowledge because we have generated the output at the bottom without using the witness, okay? That's the standard zero knowledge property. So now what is non-malleable zero knowledge? So the thing is that this game here doesn't capture a scenario that you have in the real life. So in the real life, you may have an adversary that acts both as a verifier and as a prover. In particular, in this case, you have like a left session where the man in the middle can receive a proof for a statement X. And at the same time, this adversary may use this proof, may tamper with the proof, do something strange in order to generate a new proof for an honest verifier for a statement X prime, which may or may not be related to X. Okay. And so what non-malleable zero knowledge guarantees is that if this adversary can convince an honest prover about the validity of X prime, okay, then this means that this prover, this corrupted prover, this adversary, can do that even in the case where no honest prover is providing any proof to him in the left session, okay? So in summary, this is formalized by requiring the existence of a simulator that can generate a proof for X prime without having any knowledge about the witness W, which is the witness used by the prover in the left session of the real world. Okay. So what setting? What is the setting we consider here? So we are in the plane model. So we assume no random oracle, no setup. And the type of simulation we have is black box. So you have only black box access to your adversary. We focus on constant round protocols. And in terms of assumptions, we like minicrypt in particular. The goal here is to construct a protocol relying on one-way functions only. Moreover, we would like to use these primitives in a black box way. And this is more or less the state of the art. So we had many works that try to optimize and design protocols that satisfy all these properties. And but most of these protocols are efficient but not practical. Okay? So there was a good development toward practical approaches, in particular in Crypto 2022. Kim et al. Proposed a protocol that was practical. Indeed, they showed that this protocol had just a small constant in terms of round complexity, just 20 rounds, more or less. And the prover can issue a proof in slightly more than 1.5 seconds. Okay. Now, what is interesting is that none of this work, not even these works listed in the theoretical side here, make black box use of the underlying one-way function, of the underlying primitives. Okay, so what we do in this work is to propose the first protocol that does make use of make black box use of the primitives, and moreover, it improves like the efficiency compared to existing constructions. Okay, so our protocol indeed has just 9 rounds of communication, and like the prover can issue a proof in around 100 milliseconds. Okay, and also the proof size is quite small. This protocol has other nice properties that I will list at the end. So now, how do we construct these non-malleable zero-knowledge protocols? Most of the constructions in this area are based on a fundamental tool, which is a non-malleable commit. Okay? A non-malleable commitment is like a commitment scheme. So it's hiding and binding, but on top of that, it enjoys an additional property. In particular, it has this characteristic. So you consider this experiment where you have, again, a man in the middle, but this time this man in the middle acts as a receiver for a commitment, okay? So the man in the middle receives this commitment. This is a commitment of 0 in this experiment here, and generates a commitment of some message M0 prime. So then we can consider another experiment 1, where instead the man in the middle here receives a commitment of a message M1. Okay? And again, the man in the middle generates a commitment of some message M1 prime. And usually what you require from a commitment scheme is that the commitment must be hiding, which means that the behavior, what the adversary does, what the adversary outputs must be independent from whether the adversary is receiving a commitment of M0 or M1. Okay? And so you require these two experiments to be indistinguishable. In the non-malleable commitment security game, instead, what you require is that the indistinguishability must hold even when the distinguisher has as input the message that is committed by the man in the middle on the right session. Okay? So this is the main difference. And the idea is that if you have this indistinguishability, at a high level, this means that what the adversary is committing, it's unrelated to what the adversary is receiving as a commitment in the left session from this blue party, that is the committer, okay? So this is the first main tool. The other main tool we are going to use is a Sigma protocol. So this is a 3-move protocol, and where the second round is just a random string. So it's a public coin proof system, which enjoys completeness. Honest verified zero knowledge means that you have a simulator that can return a transcript which is indistinguishable from a real world transcript where the witness is used. And we have special soundness, which means that if you have two accepting transcripts that share the same first round, but they have different second rounds, this I'm going to refer at the second round as being the challenge. Okay. So if you have different challenges, then you can extract the witness for the statement X that was proven to you. Okay, now that we have these two tools, I can show you how the scheme actually works. So this is a very simple scheme. So the prover and the verifier just engage in the execution of the Sigma protocol. And the only difference is that the second round of the Sigma protocol is computed via coin tossing. This is like a very standard like coin tossing, where instead of having the verifier using a standard commitment to commit to a share C0, we will use a non-malleable commit. Okay, so the verifier commits to C0, the prover sends some random string C1, and the final challenge, the final second round of the Sigma protocol will be computed as the XOR of these two challenges. So this seems very standard. Similar techniques have been used before, and actually this approach was proposed by Abhishek Jain and Omkan Pandey in SCN 2014. But this approach was discarded because despite it seems to be secure, it was not clear how to really prove its security. And now I'm gonna show you how actually the security proof of this scheme works. Okay. Okay, and the verifier at the end accepts if, of course, the transcript of the Sigma protocol is accepting. That's not a surprise, I suppose. So the proof approach is the following. So we have a left execution where a proof is generated for some statement X, and a right execution where the man in the middle is proving to you that X prime belongs to the lamp. So what we will do is that the first thing we do is to remove the witness from the left execution. So we will simulate this transcript. Once we simulate the transcript, we will use a proof of knowledge extractor to extract the witness for X prime. Okay, so now what we have designed here is a machine that can extract the witness W prime from X prime, and the witness for X is used nowhere. Okay? And this looks kind of like the simulator we wanted. In particular, now that we have the witness W prime, our simulator can just convince any honest verifier that X prime is in the language, because now the simulator has the witness W prime, basically. That's kind of the core idea. So let's see first how the simulator works. The simulator works as you may expect. You generate a simulated transcript for the Sigma protocol, and now you can cheat in the coin tossing because this non-malleable commitment is extractable. So the simulator can rewind the adversary, extract the challenge C0, the message, the share that the adversary is committing to. And now we can cheat in the coin tossing in a very simple way. We just set C1 equals to C XOR C0, and we simulate the proof. All very simple, all very standard. So that's how the simulation works. How does the extraction work? Also here, things are quite standard. So the extractor will do an execution like acting as an honest verifier. And then we rewind, okay? So we first collect an accepting transcript for the Sigma protocol. Then we rewind, we send a new random challenge C0, and we receive a new share C star 1, and we collect a new accepting transcript, okay? And the idea here is that we can extract the witness because we can run the special soundness extractor of the Sigma protocol, and we can do that because with overwhelming probability, we will have that the two challenges C and C star are different, okay? And crucially, this holds because of the hiding of this commitment, okay? Because note that if the commitment instead was not hiding, an adversary can always kind of force always the same challenge. So you never get in this situation where C star is different from C. But because you have hiding, the adversary cannot tweak and cannot pick C1 in such a way that the output of the coin tossing is always the same. It's always something that the adversary likes, okay? That would be bad, but this doesn't happen. Okay, so now you just need to put everything together and we should be done, okay? So again, on the left side, we run our simulator. And of course, while you run the simulator, the man in the middle is issuing his proof on the right session. And now we have an accepting transcript and we can run the extractor. Okay. The extractor I just showed you before. So you will get, that this extractor rewinds. And now you want to argue that you can extract the witness using the argument I showed you before. So unfortunately here there's an issue because before we said that you will be able to extract on the right because C will be different from C star because of the hiding of the non-malleable commitment. But I also said that on the left session, we are rewinding the commitment because the simulator, this yellow simulator, needs to extract the C0. So as you can expect, now if the man in the middle schedule the messages in a synchronous way, and it aligns the session, the left session with the right session, what you have is that when you rewind the non-malleable commitment on the left, I mean, you can never hope to make a security reduction to the hiding of this commitment because you're extracting, so there is no hiding. But the nice thing is that we said that this commitment here is non-malleable, so it has a stronger security property that we can rely on. Okay, and indeed, actually, the reduction works. So indeed, we can prove that the extraction is successful and that the challenge we get, the sister challenge we get after the rewind, is actually different from C prime. And the reduction works in this way. Okay, our reduction will just do an execution with the adversary by running the simulator on the left and just the honest verifier on the right. And now we have collected C prime, our challenge C prime. Okay, and now what we know is that if we rewind the adversary, this adversary will be able to fake and to force the output of the coin tossing always to the same challenge C prime. So what we do is that we pick 2 random messages. Those are the challenge messages for the non-malleability experiment. And we ask an external, like this external challenger to commit to one of these messages, M0 or M1. Okay, that's just a standard security game of non-malleability that I showed you before. Okay, and the middle will commit to some value that I'm calling here K0. So what we have now is that we want to use this adversary for the non-malleable zero knowledge experiment to create an adversary for the just non-malleable commitment security game. And that's what this adversary does, right? This is like, if you just focus on this like blue box here, you have an adversary that receives a commitment and issues a new commitment. Okay, that seems to be like a very good adversary for the non-malleable commitment experiment. Okay, good. So now that we have the adversary, we can show how the distinguisher works. And that's the crucial part of the proof, because we said that in the non-malleable commitment experiment, the distinguisher always gets as an additional input whatever the adversary is committing to. In this case, is this share K0. So now, because we are constructing this distinguisher, we can have K0 as part of the input, which means that we can complete the simulation and we can compute a share K1 in such a way that K1 XOR K0 will lead to the challenge C, which is like the challenge, the C value that we obtained as output of the simulator, okay? And as you can see here, I can compute the core K1 without doing rewind. Like this is just an input to the distinguisher, and now the proof is almost done, because now I received this message from the adversary, which is C star 1. And what I know is that this adversary is bad. It's bad because the XOR of what I commit on the right and what the adversary gives me, like on the right, so the XOR of MB and C1 star will always lead to C prime. But if I know this, I can easily compute what is the committed message MB. Okay, and this concludes the proof. Because now I know MB and I will guess correctly what the committed message was. So there are many subtleties here that I'm kind of not really explaining, but that's kind of how the proof approach works. And now I want to talk a little bit about the efficiency of this protocol. So I said that, you know, this is nice, this is efficient, but why? The main reason is that is related to the non-malleable commitment scheme we use. And usually non-malleable commitments are not necessarily that efficient. But the point here is that we can use a weaker form of non-malleability that, and we know instantiations that are indeed efficient. Okay. In particular, we will use for our construction what is called a weak non-malleable commitment, which is like a non-malleable commitment that guarantees you non-malleability as long as the adversary promises to always produce a commitment that admits a valid opening. Okay, and so these type of commitments have been constructed and instantiated in an efficient way. An efficient construction and practical construction was proposed by Brenner et al. In CCS 2015. And the point here is that in our construction, we can use this weaker notion because the verifier, in order to complete the protocol, will always need to provide an opening of the commitment. So if you provide an opening, then this means that necessarily the commitment is well formed. So this means that you don't need like this strong notion of non-malleability. This weak form of non-malleability is sufficient for what we need to do, exactly because we open the commitment. So we know that the commitment is well formed, and that's when kind of we will rely on the security property of our commitment scheme. Okay. So to conclude, so what we propose is like the first black box and practical non-malleable zero knowledge scheme from one-way functions. Our scheme is plug and play, so you can use any Sigma protocol. Actually, you can use any three-round public coin argument system. So for example, you can use ZKBoo, and that's how we have evaluated the performances of our scheme. And we are not done yet in the sense that we know that for zero knowledge, you can achieve zero knowledge in 5 rounds from one-way functions. or 4 rounds from one-to-one one-way functions. So the question is whether you can do the same with the case of non-malleable zero knowledge. And then the question is whether we can also get adaptive input security, parallel security, or concurrent composition. So those are questions that currently we have no idea how to answer. Okay, and that's the end of the talk. Thank you very much.
Okay, any question? Time for one quick question. So I ask a question. Do you get a proof of knowledge in the end?
Do you get?
A proof of knowledge, or is it just like plain sound?
So no, yeah, we proved that this is a proof of knowledge, and yeah, so it's also a proof of knowledge for scheme.
And is it really fast? Did you actually implement it?
Yeah, actually, we also have, I didn't show it. So we also have an implementation, a Rust implementation, where for proving just knowledge of discrete logarithm, and like it really requires just few milliseconds for the prover to issue the proof. So it's really seems to be quite practical. Yeah.
Okay, cool.
Okay,
Let's thank Michele again.
Thank you.
So we have a coffee break now. We resume at 11:10.